Hello there and welcome to one more MCTDH-X video tutorial. Today I'm really excited because we're about to set our very first quantum simulation. We will simulate few particles interacting inside a harmonic potential. So let's get started. What you need is actually a really basic thing, a text editor. Any text editor can work. My choice is a program called Kyle, which is an editor for various programming languages. I really like this guy because I can have my text here and I have my my terminal, so command environment down there, so I don't need to switch windows. But any text editor, gedit or Vim, whatever you fancy, can do the job. So first things first, actually what I'm gonna do, I'm gonna follow the first part of the tutorial as it is on the documentation of the program that is inside your documentation in the installation folder. So you can go through the PDF, okay, and have a look. So I'm gonna use the same values and we have to find the very same exact result. So let's make a directory. So I hope you can see that I am in my home directory and I'm gonna make a directory called MCTDH-X tutorial, okay, through the command environment, and then I'm gonna navigate in there. Okay, there I am. So ls to list all files, and I see that there are no files, and I'm gonna use the shortcuts that I showed you in the other tutorial. One of these is the bin cp, which means it copies the bin files. So let's list ls. So I have one library here, two executables here, fair enough, and in pcp that copies the input files. So the file that I'm gonna use is the mctdhx.imp. We want to open this file and wanna edit it. So I want to open with Kyle, and I have to go into MCTDH-X tutorial, and there are no files. Perfect. Okay, here it is. So you see that I have here the file and I still have the command environment, and you will find a list of parameters. Now I'm not going through all of these guys because you don't need the very first steps, but I will tell you only the most important, which is the number of orbitals and the number of particles here, okay, and the lambda x lambda naught that gives you the strength of the particle-particle interaction. So these are the parameters that we're going to change, and here's the job prefactor. So this is a complex number that so after in Fortran language, everything that follows this the exclamation mark is a comment. Okay, so everything here to my right are comments and are written for you to understand what each parameter does. So this is -1, 0. Then I go here and I see that is relaxation. And if I change that later to 0 -1, then I see that it's a forward propagation. So I will keep that because I want a relaxation, and I want to change the particle number from 2 to 50. So I did, and then I also want to change. Let's jump all these things and go to the integration parameters. The integration parameters are here. So this parameter defines the dimensionality of the problem, obviously 1, 2, or 3. Now I will leave it 1, and so I do one-dimensional problem. Then let's change this guy to 2, 5, 6. So in most of the cases that's a power of 2 because it's much easier, much faster for the numerical integration. And then we go to initial x. So we defined the grid. Okay, it's a numerical district grid over which the DVR, the discrete variable representation, works. And so we define that we want 205.6 number of DVR points in this x direction, and now I define the spatial extension of the grid that goes from -12 and it ends to +12. So this is what I'm changing for the time being. Of course, you're free to navigate and read all the parameters and the documentation PDF as well. but for the time being you do not need to change anything. So I'm gonna save that. Okay, and I'm going now here to the terminal, and the only thing that I have to type is MCTDH-X. Let's type enter, see what happens. All right, I get some messages, and this means that it works and that it calculates. So it has started doing some stuff, and you have to wait some time. That depends. Okay, it goes further depending on your processor and your memory, of course. Now let's wait a little. Okay, that's important. The propagation has started, so it's propagation in imaginary time. So the last column that you see here is the energy. So at every step the energy of course decreases until it goes to a value that does not decrease anymore, and this is where we say that the value, that the problem has converged and we have found a relaxed state. This means that if I propagate then in real time, the state will not change. So I have to wait some time, few minutes, until this changes. This energy, is not changing anymore.
Please hold to speak with a patient service representative.
A good 3 hours, and I'm still not through. So probably you might need to wait until time 20 or so. Now will show you what we have obtained and how to visualize it. So we have the solution of the system of 50 particles that are confined in one the harmonic trap. They interact with interaction which is we chose here, which is relatively strong. And now we're gonna see what MCTDH-X gave us as a result. So first thing is the NOPR.out file that gives us the natural occupations of the natural orbitals of the system. So tail that in order to get the very last line, and this gives us the time. So the last time, about 20, it's enough for this problem. And then the next 4 columns, this is so the very last row of a series of columns. The 4 columns are the natural occupations of each orbital, beginning with the least occupied one, so that's time minus 2, and everything is normalized to 1. So the maximum, so the summation of that will give me 1. So the largest occupation number is 0.96, which means that the system is 96% condensed. Okay, so in that system, and I should have expected that because it's a single harmonic trap, I'm very close to condensation. And the last column that is down here is the energy of the system, and you do have to find the very same energy, at least to accuracy of 7 or 8 digits. So you should compare to that value. So let's plot, and let's also see what kind of files we have. So there are many files because they the step for printing the files was very small, and this is the dat file that contains all the information for the coefficients of the many-body expansion, and these are the files that they end in orbs.dat, that they contain the information for the natural orbitals, actually the real and the imaginary part of each natural orbital, and the density, and also the potential. Now the description, and this is the time, okay, in front of that. The description of that is in the documentation PDF in your installation directory. And let's go and plot these guys. In order to plot, we use the program GNUplot. Probably you have it already. If not, you can download and install easily. It's open access, open software. So we'll take the last file, which is 20. Okay, so tab to autocomplete, plot, so quotation, and 20 orbs autocomplete. Then I have to close the quotation, and then I have to tell GNUplot which columns should take in order to give me a plot. So I type U for using, 1 because, so that's the structure of the file. As I told you before, go to the documentation and have a look. 1, 2, 3 is X, Y, Z respectively. So we want one dimension, we need only X, so that's our X label, and the second would be 8 because 8 is the density, so that's the average density over weighted average, let's say, over the natural orbitals. I want to normalize that. It's not necessary, it's absolutely not necessary, but I want to normalize that with 50, which is the particle number. And I will also plot the potential. In order to plot the potential, actually you don't have to type the whole file name, just quotation, nothing, close quotation, and then it will take the previous file using 5. Okay, so I will take the 5th column and I will see what happens if I plot that. So I take where it makes sense. It's a harmonic drop and it's something like a density. I don't like the plot range, so I'm gonna change now the plot range. Okay, so X take all, and on Y take all up to 10. Okay, so now I see that better. That's my potential in green. If you want to plot it with connected lines, then you use WLP, and that's the potential, and that's my density. And let us plot some of the natural orbitals. The natural orbitals I'll put on at the very end. Again, same file, at the very end of the file. So I will take columns 24 and 25 because these columns correspond to the, so these are the last columns on the file, but they correspond to the first natural orbital. That means the natural orbital with the highest occupation. So I have to do 1, and then I need to take my normalization, which is 50, and then I need to take square root and column 24, which is the real part of the first natural orbital, squared, plus column 25, and I have to close the parentheses, and let's take one more. That would be the same file. Okay, I will take 20, not I took here 24, 25. I will go to, okay, normalization, squared. Now we'll take 22 and 23. I hope I didn't mistype anything. Let's have a look. Oh yeah, now it does look good. It does look good. So that's the drop, again the green one. This is the density. So I hear a little deepening here in the center, and this deepening comes from the fact that I have a tiny little bit of fragmentation, which is not 0. And this is a very interesting thing. The blue one actually is the first natural orbital, and the yellow or orange, as you like, is the second natural orbital, and we have another 2 natural orbitals in the calculation, which I'm not plotting here, but you can experiment at home. So, congratulations, you just did your first calculation with the MCTDH-X, and if you like this example, then stay tuned because many more interesting things, including fragmentation and transition from condensed to fragmented states, will follow in the next video tutorials. And until then, enjoy MCTDH-X.